Hello, everyone. Let's discuss another Leetcode problem. Today's problem is problem 55, jump game. So the problem description says you are given an integer array, nums, an integer array. You are initially positioned in the first index. So say if this is my integer array, I'm positioned in the first index. And each element in the array represents your maximum jump length at that position. Okay, so if I am here, that means I can jump maximum of 2 steps, or I can also jump 1 step, right? So I can maximum jump 2 steps. We have to return true if we can reach the last index. So our target is reaching the last index by jumping, right? Okay, so you see here that I can jump to, say, here, or I can jump here. From here, I can jump like 3 steps. You see that? So as you can see, it's possible for me to go to the last index. What I do is I jump from 2 to 3 and then 3 to, sorry, I jump from index 0 to index 1 and index 1 to last index, which is index 4. Okay, so this is pretty much possible. In the second example, you see I can jump to index 1, I can jump to index 2, or I can jump to index 3. But if I jump to index 3, I'm actually stuck. I cannot go anywhere. Okay, so let's see if we can do anything from here. From here, I can maximum jump to this or this. So this is useless. But from here, from index 2, I can jump only to here. That means anyhow I jump, I am going to get stuck here. And from here, there is no way to jump. So I won't be able to reach the end. So here are two small examples where we can actually manually try to find out whether we can, from our first index, can we jump to the last index or not, but how to solve it programmatically. Okay, so let's think about the solution approach. Okay, so the first approach that I'm going to talk about is we can actually use a dynamic programming approach. That means, say, let's think about this. If we have a cache or we call it like memory or something. Okay, so we have a cache and then we identify some good spots. Good spots means if we reach those spots, from those spots we can jump to the final index. So you can see here we'll keep flags from each index, from each position, and try to see if these positions are good index or like good positions or not. So let's start with the easier way, is starting with the last index. So if I am in the already in the last index, is it a good index? Yes, obviously this is a good index, right? Because if I'm in the last index, then that means I'm already there. So this is a good index. So next, what can I do? So next, what I can do is I can start from this index and see that within my jumping capability, like what is my jumping capability? My jumping capability is 1, right? This is my jumping limit. So within my jumping limit, can I reach a good spot? If I can reach a good spot, then I can say, oh, I am also a good spot. That means from me, anyone can go to reach the end. So you see my jumping capability is 1. And after jumping 1 spot, I reach the good spot. So that means I myself am also a good spot. Okay, you see that. Next, let's see from the next index, what is my highest jumping capability? Well, this is my highest jumping capability, right? And now you see that although I myself cannot jump, this is not possible. Although I myself cannot jump to the end, I can actually jump to a spot which is a good spot. That means If I reach this point, then the next thing will be taken care of. So that means I am also a good spot, right? So next, my jumping capability is 3. That means I can jump all the way here. Now, if any of these 3 are good spots, right? If I can jump here, that means I can also jump these places. So if any of these are like good, then I am also good. So that means I am also a sweet spot, right? You see, all 3 of these are good. It wasn't necessary for all 3 of these being good. I could just like go to any of if any of them was good, I was fine. Okay, next you see my jumping capability is 2. That means I can go all the way to here, maximum. I can go here as well. So both of these are like good spots. That means if I jump to any of these, I'm fine. That means I am also good. Finally, once I reach the first index, the 0th index, I will check if I have turned into a good spot. If I'm in a good spot, then I'm done. So you see, we are keeping a cache and we are fine. Okay, so let's look at the next one. Okay, so here are a few things. Say if this was 4, right? So in that case, what would have happened? You see that my jumping capability would have been like far away, but I don't need to check all these way, right? What I can do is I can just take the minimum of uh, sorry, the maximum of the minimum of my jumping capability and how far I am from the last spot. I will check all those. And another thing you see is when I am actually filling up this memory from here, when I am in this spot, I have to check all the way. In the worst case, I have to check all the way to the end, right? When I am here, I may have to check all the way to the end. Similarly, when I'm here, I have to check all the way to the end. So in theory, I am checking like in spots, like, right? And for each of them, I may need to check, say, when I'm here, right? I may need to check all these, like potentially I may need to check all of these, right? Okay, so that means for each of the indices, I may have to check all the spots in the array. That means n, for n spots, each of them checking n other spots, the order is going to be order of n square, right? So let's try this dynamic programming approach for the second problem. You see the second problem is 3, 2, 1, 0, 4. Okay, and then we'll have this cache. Okay, initially you see that this is fine, right? The last index is a good spot. I have already reached there. The second one, you see, it doesn't have any second last. The second last doesn't have any jumping capability. So it can't reach any good spot. So we are stuck. Now the next thing is, you see here for the third one, it will check only here, like is jumping capability is maximum of 1. So that means it cannot reach any good spot. So it is also gone. Although these two are like crossed, that means from these two spots, I cannot reach to the end, but we are not actually given up hope yet, because there are chances that we still will be able to reach a good spot. Okay, so next, from here I can go like to this spot, jump to these spots, and both of these are like bad spots. That means I'm out of luck. From the last one, you see I can jump to these 3 spots. All of those are like bad spots. That means there is no chance that I will from the first spot I can jump to a good spot. That means I cannot jump to the last index. Now let's change this input to a little bit. If we had changed this thing, say, to 4, in that case, you see that my jumping capability would have extended to this. And I just need one good spot, right? So I can just, you see, I have one good spot. In that case, what would have happened is I could just, this would also would have been a good spot because I could just take this jump, right? Okay, so that's the dynamic programming approach, and this is order of n square, all right? Now let's talk about a clever way of doing it, which is going to give us a very optimal solution with less, even with less memory, utilizing less memory. So the observation here is the observation for you. The same thing, let's look at the same thing. So you see, when I changed this input a little bit, but can you see this, like every time, say for the first example, for this example, when I was checking, say, okay, so this one was 1. Okay, so when I was checking here, right, I was checking all, I can check all 3, but basically I don't need to do that. What if if I knew that my nearest good spot, say nearest good spot, this is my nearest good spot. If I can jump to my nearest good spot, that's fine, right? And obviously, if I have more jumping capability, I can just go beyond that. But why don't I just focus on my nearest good spot? And if I can reach there, I'm fine. Okay, so using the same idea, let's say we say that this is the nearest good spot is index 4. This is the nearest good spot. We start from here, right? Okay, so when I come here, I say, okay, can you go to the nearest good spot? It says my index is 3 and I have a jumping capability of 1, which is equals to 4. Yeah, so that means, yeah, I can go to the nearest good spot. So I'm also good spot. So I can say my nearest good spot is now index 3. Okay, so now I check here. It says my index is 2. I can jump 1, which is 3, which is equals to 3. That means I can go to the nearest good spot. That means I am also good spot. So my nearest good spot now becomes index 2, which is the nearest good spot. Okay, so I come here. Next I check, hey, my jumping capability is 3 and my index is 1. 1 plus 3 is 4, which is greater than 2. That means I can even go to the 4th index. That means obviously I can go to the 2nd index. I don't need to go to the 4th index. Even if I go to the 2nd index, I'm fine. I can jump to the 2nd index and rest is taken care of. That means I'm good. So my nearest good spot is now index 1. Okay. Next, let's check this. So my index is 0 and I can go jump maximum of 2, which is 2, maximum of 2. 2 is greater than 1. That means obviously I can jump to this index 1. That is fine, right? So if I can jump to index 1, I'm fine. And I can jump to even to index 2. That means my nearest good spot is now index 0. So index 0 turning into a good spot means I can successfully jump to the last spot, right? Similarly, for this one, I don't need to keep this memory. I just keep my target spot as the last spot, 4. This was 3, right? I make my target spot as spot 4. Hey, can you go to 4? No, it cannot. It cannot. So nearest spot remains 4, right? Target spot remains 4. It says I cannot get to 4. So no, there is no update. So I go here. Can you go to index 4? It says no, I can go to index 3. I cannot go to index 4. So index 4 still remains the nearest good one. I go here, I ask, hey, can you go to spot index 4? It says my index is 1 and I can jump 2. So I can maximum go to index 3. Still, I cannot reach index 4. That means still the nearest good spot is going to be index 4. Finally, this one, it says my index is 0. I can go to maximum of index 3. Well, still I am short of the nearest good spot, that is index 4. So I failed. That means I cannot get to the last spot. Okay, so what is the time complexity of this algorithm? You see that I am just keeping a nearest index, right? That's a constant memory. No memory, extra memory is being used. And the other thing is, when I am actually checking here, say I'm checking here, right? I'm not going to check everything. I'm just checking against the nearest spot. So when I'm actually going to every point, I'm just making one comparisons against the nearest good spot. That's it. So in total, I'm just going to n spots. I'm doing just n comparisons. So sorry, one comparison. So every spot, I'm just making one comparison to see if I can get to the nearest good spot or not. That's it. So it's order of n algorithm. So this is the greedy approach, and we're doing it in order of n. Okay, so let's try to code this. Initially, we'll say like good spot means say target, or let's say good spot is nums dot length -1. That is the last index. That's a sweet spot, right? And then I will start from int I equals to from the second last spot. I greater than equals to 0. That's the end condition. And every time I will just go one step back and I will check if my current index plus my capability of jumping is greater than equals to the sweet spot, right? The nearest sweet spot. In that case, I will just change the nearest sweet spot to my current index, right? Yep. Okay. And finally, I will check if, okay, return. If the nearest final good spot is going to be turned out to the first index, then I say, okay, from the first index, I have the first index is a sweet spot. That means if I'm in the first index, I can jump to the end. Okay, so let's fix this. We have put a method. This is an array, so it's not a string or something. So you just fix this and we run it. And this is pretty fast. And you see, this is an order of n. We used greedy method to solve this. So we'll come back with another problem. Thanks for watching.